Hello, everyone.
Paolo, how are you?
Hey, JP. I'm fine, thank you. Okay, so welcome, everyone. I think we can slowly start. Maybe we give one more minute. I see people joining.
Yes, hello. Hi, Paulo. Hello.
Hey,
Yeah.
I see some
See,
newcomers. Welcome to the newcomers.
yes.
This meeting. Let me start by sharing the screen and putting the slides on the. Okay.
Hello, can you hear me?
Hello?
Yes. Yes.
Great.
Yes. There
Good
was just no one talking
morning.
right now, I guess. Yeah.
Good morning, good afternoon.
Yeah.
Yeah.
So I see
Antonello,
people
hi. Yeah.
are still joining. So let's get slowly started with a warm welcome to all the new people to this call. So good morning, good afternoon, good evening, wherever you are in the world connecting to this call, which is the fourth call of our sub-project, power distribution. So I was just reflecting this on this before opening the call. So in 6 weeks, we are at the fourth call. All the work streams are up and running. So I think we're moving pretty fast here. So I'm really happy about this. We are now in excess of 400 people subscribing to the mailing list. So we are in this sub project is in the top of the open compute community. So it's also very nice to see the interest on the topic. So for today, we are going to give a bit of space to an important topic because data centers are a relevant load seen from the grids. And they are expected to become even more relevant considering the amount of power. So we will give a bit of space to the TSO perspective. So we will have a special guest today, and then we will have a bit of an update from the work streams, which I said have been starting. So they are already working up and running, having working meetings with people willing to contribute at different levels. So we will hear from them. So this is more or less let's say the high level agenda. We will have Eric Meyer. I hope you are on already for half an hour, including a few question and answers.
Yep. I'm here.
Thank you, Eric. Before we switch to your presentation, since there are newcomers, I take the opportunity to remind that all the workstream meeting invitations are available in the project calendar you find at the bottom of the sub-project page. Always refer to this one to find the latest and greatest calendar. And second, in the wiki page, which we are keeping up to speed, you can find the working folders, so the public folders of the work streams. Reach out to the workstream leaders if you have questions or if you want to contribute in a deeper manner. So that's more or less the introduction. So I would say it's time to, unless there are additional remarks, I don't know, JP, if you want to add anything. Otherwise, we can give the stage to Eric.
No, I think it's just grateful for everybody's efforts. Paulo in particular as pushing everything. The key here is just if we can get to that outline and that work by before the Christmas holiday, I think that's going to get us to a significant milestone, and then we can continue on, but we'll talk about that later. I'll yield the floor back.
Good. So Eric, stage is yours.
All right. Am I able to share? Oh, there we go. Okay. Thank you all for the time to present here. I know, this may be a little bit of a topic that's new to you, or if you're like, hey, how does this even matter to me? And so that's what we're going to hopefully cover, and then look at some of the emerging requirements. So what we're going to discuss today is, what are sort of the impact of large data centers on the grid, and then what are really the emerging requirements that data centers are going to need to meet in order to be allowed to be connected to the grid. Now, I'll note that not potentially, there's going to be multiple solutions for each of these items, not all of which may be in scope for the power distribution subproject, but I will lay them out there because you may have more innovative solutions than I do. I am not an expert in the power distribution subsystem. So we'll talk about voltage and frequency right through what we call post-fault active power recovery, protection system coordinations, and how you program your protection systems in order to safeguard your facility. And then what we call oscillation and ramp, which is, what is the real power consumption of your facility and how fast can it, that output change. And then some notes on control and monitoring methods. Now, I'm going to issue a disclaimer. Every system operator and utility has different operational philosophies and protection philosophies. This information is here to convey concepts. It is drawing upon the real requirements and proposed requirements where available, but note that some of these are proposed and may be subject to further change. Okay, so just a quick slide on, why does this matter? Traditionally on the power system, loads have been a couple hundred megawatts at the largest size. We are seeing data centers reach, 500, 600 megawatts with hyperscale facilities, along with gigawatts size. There's about 5 or 6 gigawatt facilities expected to be energized in North America in 2026. And then, we are seeing requests of facility sizes of 5 or 6 gigawatts or larger, which is much larger than anything historically that's been connected to the grid. Our largest generator typically is around the 1 gigawatt size, and as we see load that begins to eclipse this, the loss of such a load will trigger high frequency and voltages. Hey, Ashish, are you able to mute?
With regard to this, I know we don't have a.
Can everybody go mute, please?
Thank you. So the disconnection of a data center from the grid, whether it's intentional or unintentional, can create reliability risk. Sudden disconnection can lead to high frequency and high voltage on the system, which could potentially trigger protection systems and leading to cascading outages. That's where the loss of an element triggers the loss of another element, resulting in the system blackout. We don't want a system blackout. I am hoping none of you do as well. We want to keep the lights on. We want to ensure that power is delivered to all the customers so they can keep using all our technology. And this can be excavated by insufficient post-fault active power recovery when the load did not return quickly enough, and then miscoordination of protection systems. And then the repetitive patterns in load consumption can cause oscillations on the grid, which can damage generators. We'll delve into a little bit of each as we go forward, but this is just sort of the high level. So the biggest issue that you'll see from grid operators today is right through. Now, I presented this slide before during the call, but every day on the system we experience a fault on the grid. This could be, a car hitting a pole, a lightning strike, a tree hitting a line. There's been examples of an overloaded crane has hit a distribution line, which then fell into a transmission line, or a train hit something. These may seem like this is never going to happen, but given the large scale of the system, they happen every day. And during this case, we see a fault on the system that triggers breakers to open. And during this fault, the voltage dips, which is seen by all customers in the area. Tony.
Hey, Rick.
Question.
Quick question here is because I've been reading a lot of things around, a fault statistic on the grid, and I read here you say, the equipment to connect to ground. Is it the highest percentage of fault to ground? That's what I read, but I would like to get your feedback, for curiosity.
So there's several different types of faults. We can have we run a 3-phase power system. So single phase to ground, 2-phase to ground, 3-phase to ground. The 3-phase to ground fault is going to have the highest fault current contribution. There's also phase-to-phase faults as well.
Okay. But do you see, Mark, a phase to ground, 1 phase to ground fault? This is the
Yeah, of one phase to ground fault will be
Okay.
more common.
Thanks.
And so similarly, if we lose a generator load, we see frequency imbalances. So every time on the power system, we have to ensure frequency matches generation, and that's 60 hertz. And, if there's a large swing in that, we can see a frequency right-through issue where equipment needs to be able to withstand these deviations. So right-through is the ability of equipment to withstand deviations. JP?
Yeah, you might have it in the slides later on, Eric, but if you could just walk through that, what happens to the grid? So say hypothetically there's a auto recloser that hits 3 times and it triggers a brownout situation at a data center in a large scale. What happens to the grid? And you can walk through the dangers specifically, because I think we know there's a thing there, but the first principles behind it for common understanding for this group might be good for you to share your knowledge. So everybody has that common understanding of why it's such a significant issue and why fault ride through is a big deal.
Yeah. So I don't know if I have all the details in the slides. I may have some of them pieced together, but so yeah, let me get to that. So what would happen in the past is, if we lost a single load that's 5 megawatts, that's not an issue. We would not see a large frequency deviation or voltage deviation. But what we see is, we have an area, when there's a fault, there's an area that will be impacted by the fault. Now, this varies under certain parameters of the power grid, but, and so the area may be larger or smaller. Now, what we're seeing is that when there's a fault, the voltage will dip low enough that multiple facilities will see a voltage dip below, say, 0.7 per unit, at which point they transition to UPS and then to backup power potentially. When we have 5 or 6 or 7 facilities do that at the same time, we have such a large loss of load on the grid that we need to balance load and generation. If you imagine a scale, they must be equally balanced. All of a sudden, we have load that is much lower and generation that's rising. Our frequency will begin to increase, and the faster frequency, the higher frequency goes. If we hit a limit around 60.4 hertz, turbine generators will begin to go offline, because if they spin faster than that, they will damage themselves. And this is just, pure physics on the design of the generators. They can only withstand a certain speed before they hit their essential material limit. And we don't want that to happen, because otherwise they blow up. We can't serve power. And if we cannot arrest that decline in time, the entire system begins to collapse. So the reason that happens is if we lose those generators, we then, we have too much generation, too little load. It starts to shift. We have too little generation, too much load. As that goes, all of our equipment inside our houses, inside our facilities will be damaged if the frequency is too low. So we have and if the voltage is too low. So we have systems on the grid under voltage and under frequency load shed that will immediately start cutting people off from power. And that's a last ditch attempt to save the grid. If that doesn't work, you saw what happened in Spain earlier this year, where there was a blackout and they lost power across Spain and Portugal. That is what we're trying to avoid.
Yep. And then can you detail a little bit more, right? So like, I think at least when I was in generation almost 10 years ago, every midnight or around that time, I would get a call to adjust my power factor on my generator to share reactive load throughout the grid. What happens to that power factor when a large load drop occurs like that?
So generators these days, for the most part, that's all automated. So they are responsible for maintaining the voltage at what's called the point of where they connect to the grid. And so they have some automatic control systems to manage that in real time. That setting is being adjusted throughout the day to adjust the increase in real or reactive power to either absorb or inject it, depending on what the system needs. So the transmission system operator will tell the generator, hey, we need you to maintain a higher voltage at the point of connection or a lower voltage depending on the needs of the system. So what does a data center do? The data center has more load on the system. It needs reactive power to support it. So you may see, generators providing more reactive power, but that is very dependent on the load of the system, the topology and the configuration. Is reactive power more local than real power. So it's harder to make a say there unless you're directly co-located with the generation facility, which means you're installed right next to it, not like co-location server facilities. Now, we've done studies to say, hey, if we improve the grid capability, can we resolve these issues without needing improved ride-through from the facility? And the answer has been no, unfortunately. While it can be somewhat improved, the risk is still present. And, at least in the ERCOT region, we see that if we lose more than 2,600 megawatts of load at once, we will lose control of frequency stability. That number is still pending some final studies, but the initial studies have shown 2,600 megawatts. And we already have locations where we have multiple facilities, that want to energize in that area. And if there's a fault in that local area, all these facilities are going to hit, say, 0.6 PU and transition to backup power. There's more than 2,600 megawatts, and so we lose frequency control. So really what the studies have shown is we need better ride-through capability in order to ensure grid stability. To that end, system operators across the world are PSOs are proposing standards. So first two are ERCOT, which is a proposed standard, and the Southwest Power Pool in the middle of the United States. I am not going to read through all of these, but ERCOT, is we define continuous operations, and then at certain voltage limits, how many seconds you must stay online. SPP is doing the same thing. You can tell they're pretty similar, but not the same. And then SPP also specifies transient overvoltage requirements as well. So for ERCOT and SPP, both of them between 0.9 to 1.1 per unit, and the voltage is continuous operation. Now, at 0.8 to 0.9 for SPP, you have 2 seconds, but ERCOT, and same for ERCOT. Now we start to diverge at 0.7 to 0.8 for SPP. They must withstand that for 0.5 seconds. And then in ERCOT, from 0.5 to 0.8, you must withstand that for 0.5 seconds. Now, something to note is, at least in the ERCOT region we've discussed, is there is a difference in the fault location. If the fault happens right outside your data center, your voltage is basically going to go to zero, and you're not going to be able to ride through, most likely. But if you're several buses away, you will see a fault decrease and so forth. Now, folks are also proposing frequency ride-through. This is probably less of a concern, but it is just something to, call out. And you'll see that there's different frequencies bands that each people are proposing. So ERCOT, you need to ride through from 57 hertz to 58.8 for 299 seconds, whereas SPP is only from 58.8, to, at 299 seconds. Now, there's other additional grid operators. FinGrid on the left is the Finland operator, and AESO is the Alberta Electric System Operator in Canada. Unfortunately, FinGrid did not publish theirs as nice, easy tables to read, but AESO is done, and you'll see that their voltage triggers are different, and their timing is different than ERCOT and the Southwest Power Pool. Same with their transient overvoltage requirements and the frequency requirements. So the frequencies are more similar to ERCOT. And one of the things to take away is everybody's power grid is a bit different based on what's connected to the system, its resource types, its engineering. these are not going to be the same across the world, which is going to be a challenge for everybody. And then your grid, which is in Ireland, had your proposal, also a graph, not necessarily a table, and they are specifying, how quickly the load must return to service, essentially. Now, one of the other concepts that we need to talk about is post-fault active power recovery. So what this is how quickly the facility returns to the grid following a fault. So if the data center disconnects, either switches to UPS or you want to backup power, you must restore the load quickly, else we jeopardize frequency stability. And if we jeopardize frequency stability, we have a situation where we have a large mismatch, protection systems are going to trigger, and potentially we could lead to a blackout. So in Finland, they are requiring that data centers above a certain size return to post-fault or pre-fault active power consumption in 0.5 seconds at a 90% level. ERCOT is saying you must return to 90% active power pre-fault within 1 second. Alberta is saying 100% active power pre-fault within 1 second at the default setting, but that should be configurable between 1 to 10 seconds and depend on grid conditions. And then Energonet is saying 80% active power pre-fault within 5 seconds and then 90% 30 seconds. So, this is going to be the challenge of how fast can your monitoring and control and monitoring settings detect the sort of heartbeat signal from the grid and then start re-energizing and bringing servers online. And, at 1 second, we're talking probably 0.5 seconds for heartbeat detection and 0.5 seconds for server booting and startup, which is pretty quick. And I believe that is faster than what most people are doing right now, at least from what I've been told. So that is going to be a challenge, right? There are ways from our perspective, we don't care how it's met, whether it's the server starting up, whether it's a battery starting to charge, or whether you throw a giant resistive load bank in. However it works, it works. And that's, one of the beauties for us. We don't care necessarily what the end product is. We do care from a sense to making sure that we model it appropriately in our studies. The exact technological implication, method is up to you all, the experts.
Okay, so Eric, maybe this is an important point you mentioned last. So your vision is at facility level. So whatever the method is. So what this sub-project could be interested is the potential, let's say, consequence of those requirements on the LVDC system. So that's the perspective we are listening to you.
Yes.
Yeah.
And now I say that there are some minor cases where we are concerned with what the method is, especially if we get into what we call electromagnetic transient modeling and some very specific studies. But for the most part, like big picture. Now, the other thing to discuss is protection system considerations. I'm not going to say y'all are doing this. I know some facilities are, but we've seen events where there are protection schemes to count the number of voltage disturbances on a grid and transition to UPS and potentially backup power if there's a certain amount of disturbances within a certain time frame. And we've seen, 3 disturbances within 60 seconds and so forth. So just some background, right? When there's a fault on the grid, breakers will open to protect the element, and then they will eventually try to close. So this is what we call high-speed reclosing, and they will see, hey, is the fault cleared? Because let's just say it's a branch hitting a line temporarily in the wind. Oh, it's gone a second later, right? It's going to attempt to reclose and restore power and flow. So after the fault is there, high-speed reclosing will attempt in the 20 to 30 cycle range, and then they will typically do 1 to 3 attempts afterwards. If you have a transmission line, there may be reclosing at both attempts. So when we say 3, you may see 6 shots. We call them 6 attempts. Now, that's something that, just how the system works. The other part is breakers require times to operate, which is about 40 to 70 milliseconds. And then if your protection scheme does not account for breaker tolerance, these timing tolerances, it may misoperate. So if you set a count the voltage depression at 80 milliseconds with a plus or minus 20 millisecond tolerance, then you would operate if the depression was 60 milliseconds, but that's within the timing of the potential breaker operation. So ideally, you do not count something until it's outside that breaker operation window. Now, this is from Dominion, that might be a little bit variable per the local utility. And so this is just general concepts, not necessarily you should all do this number exactly, but it is something that ideally is configurable in the design, right? And something that is acknowledged and thought of. So as far as requirements, the Southwest Power Pool is saying that minimum of 6 attempts within a 90-second period. ERCOT is proposing that you shall not implement this scheme basically at all. FinGrid is saying that you shall write through 10 100 millisecond bolted faults during a 90-second period in your grid. I copied the wrong sentence there. Well, no, this is what they had, which returned to pre-fault conditions and remain above 95%. So that is something that needs to also be thought about. Now, oscillations on the power grid, this is essentially a repetitive behavior in the load or voltage, of the equipment. Typically, we talk about generators and loads in this case. So by repeated load fluctuations, which we can see in AI training or just normal operations of a data center, we can drive what's called a forced oscillation. And then, these forced oscillations especially can lead to, if they're subsynchronous, especially generator tripping, interactions with the generators that damage equipment, and then the tripping of a generator. We've seen this in North America already. Here's an example of some really repetitive demands that was a subsynchronous oscillation. Now, you could address oscillation management at several levels of the data center, and really, I'll leave it up to you what makes the most technical and economic sense. So you could absorb power, with energy storage, absorb and generate to offset this. The NVIDIA GB300 NVL72 has the power smoothing function at the UPS sidecar level, and then at the facility level energy storage paired with a solid state transformer. Maybe there's other ways to do it. I'm going to leave that all up to you. You could also have resistive load banks to help absorb power, and backup generators to generate power that's just not energy storage. So there are ways to mitigate these oscillations, but it is something that will need to be done. Now, Alberta is saying you must limit load ramping and you must limit that net variability, which is essentially oscillations. Same with FinGrid. FinGrid is saying, fluctuations in active power must be controllable, and same with AnchorNet. So these are not requirements that are just, it's a theoretical risk. These are things that we're seeing. And with the ramp management, ramp is how fast the facility can move up and down. There are concerns on we maintain adequate reserves in the power system to be able to handle these fluctuations. But if there's a lot of data centers in a system doing this all at the same time, we may not have adequate reserve to handle everybody doing this at once. And on our side, we're trying to balance the solution that is the most reliable with the least cost to customers. So while we could be able to say, yes, everybody could do it, and we could procure reserve to do that, consumers are going to be paying through the roof, including you all. So it's really trying to find that best balance between reliability and economics. And then we'll get to the last part in 30 minutes. This one I just thought I'd call out. It might be interesting. The Southwest Power Pool is going to require that during a disturbance, data centers use constant current control and not constant power, which can result in increased current draw during voltage sags and excavate reliability issues. And then we've noted that in a lot of systems, high quality a lot of events, high quality monitoring is necessary. So whether this is on the data center side or the TSO side, a grid operator side who actually installs equipment like phasor measurement units or digital fault recorders, but Alberta is saying data centers shall have them. So something that'll probably be useful on your side is high quality monitoring, so you could see what's going on within the facility and be able to assess. Now, there's a lot more good requirements than just these. I highlighted a couple that I thought would probably be of the highest urgency based on what we're seeing from, the North American Electrical Liability Corporation Large Load Task Force and actual events in the field from system operators and TSOs. And then sort of to summarize and conclude, you're going to need to be able to meet these requirements, or you'll not be allowed to connect to the grid, or will be allowed to connect at reduced levels. There are multiple paths for addressing these. Some of them may be in scope of this OCP subproject, some of them may be out of scope. And I'm going to leave it up to you to determine what the best approach is. And really, it's what is the best technical and economic solution. And ideally, you look at these with a whole systems approach and don't just say, this is my personal thought. Don't just say energy storage can do it, because maybe it can, and maybe that is the best solution. But don't forget, there may be other methods to mitigate these that are lower cost, more reliable, and y'all are the experts that can hopefully help figure that out. One of the things that I want you to take away is different grids will have different requirements. So at some point, ideally these are sort of configurable and modular. Oh, I need a certain amount of capability. I just drop in another block, right, of whatever the solution is, and I've got my configuration, and I can just program the software to do that. And then we'd like to see as much information on this as possible in public forums. OCP is great. I know there's been some discussions on the solid state transformer side, because ultimately we will need some of these details in designing our dynamic models and electromagnetic transient models. Granted, we would like you all to provide some of those models when the time comes, if not most of them, but we do need that information to sort of assess what's going on, verify, and figure things out. So thank you. Hopefully I stuck to 30 minutes.
Sure.
Rajesh?
Can you go back to
Yeah.
the slide of the key points? I think that would be a good place where we can jump off of. I think Rajesh has his hand up, but I think before we get into that, if this is not achieved, right, and we don't have some mitigation for fault ride through, from my understanding, you're the expert here, Eric, so please correct me. Effectively, if the grid has to do this, that increases the rate case for everyone, which means all the taxpayers and the constituents that vote will have to pay more money, and that creates a NIMBY issue for data centers. I think that's the large risk outside of the fact that you could also go in the dark, assuming that we fix the problem somewhere in the chain.
Yep.
If we don't do this, everything goes in the dark like Spain. And then if the grid or the operators have to do that, that raises the rate for everyone, which then creates NIMBY for all the constituents of people who vote. And then there's potential for more drastic actions that will be imposed upon the industry. That's the macro things that I'm hearing. Is that accurate, Eric, or can you comment on that?
Yeah, I would say that's accurate. There's a few things there, right? It's going to depend a bit on the grid to grid and, country to country, and not all the same. But I think the first thing you're going to see is your data center is just not going to be allowed to connect to the grid. If you want grid power, you built the asset, you can't turn it on. I don't think you want that, but I'm not the expert there. So that's going to be the first one. And then there are some regions where if it's already online, or you will be allowed to connect, but you will be curtailed first. You will be turned off. You may have your operation dictated to you in a way that you do not want. And then definitely too, right, is while there are transmission improvements that can, play a role in increasing limits and what the grid can support, ultimately, who pays for that is a big issue. I I'm not going to attempt to assign costs, but that's dependent on jurisdiction. But definitely, all the points you made, JP, are very valid. There's could be pushback from folks who don't want this in their backyard, issues over cost allocation. Constituents will speak to their elected representatives, regulatory bodies, and I think that is a concern you would have to navigate, yes. And if it does go black and it comes out to be the cause that, this obviously it'd probably be a multifaceted cause where the system didn't react appropriately, but the triggering event was, 4 data centers going off at once. I don't think anybody's going to want to hear that. Just say that.
Yeah, and then I think the other piece here is, do you have a timeline that you are aware of, and or is there a size of data center that's already been discussed on your end, or any insights on that?
Yeah, so timelines are going to vary from grid operator to Southwest Power Pool has already approved their requirements, and I don't know if it's retroactive or not, or what the technical effective date is, but ERCOT is proposing our requirements into our stakeholder process. It could be they would not be retroactive. It would likely take effect in 2028. But that's all pending the stakeholder process. For Alberta, FinGrid, UGrid, a lot of those are working drafts, or I'm not as familiar with the European grid operators and their policies. So, but yeah, I would say it's coming. If it's not here already in the next year or two, at most, because we've already seen these events on the grid, and there's already these concerns.
And then you didn't mention these, but I can
Oh, the
extrapolate.
size limits. Sorry.
Yeah.
I'll just take the size limit. That's different for everybody. ERCOT is looking at 75 megawatts. Others will look at 20 megawatts. Others will look at 200. And so I think it's going to need to be configurable on your end, where ideally you want to just have a single, solution you drop in. You don't want to have to do something different for everybody.
And then you didn't mention the pieces, but I think this also applies the stringiness of the Australian grid. It applies to Malaysia, Singapore, Indonesia, any other places where there's a ramp, Dubai, Saudi Arabia, anywhere we're going to be going. If it hasn't hit yet, it's just because they haven't seen the symptom yet. Is that an accurate statement, or I just don't want to speak for you though?
Yeah, and as far as Australia, they just released something today or yesterday. So, they're moving forward with these requirements as well. So, yeah, all of these folks are, if it hasn't hit yet, I know they are looking at what's going on in North America and Europe.
Okay, there are a few questions, so let's give space to them, maybe, and trying to carve out some space for the workstream updates. So I think Rajesh.
Yeah, hey, Rajesh from Oracle. Eric, thanks for the presentation. Very relevant, timely topic, and thanks for spreading the word. My question is on the ramping requirements. The current requirements that are proposed by ATC is extremely onerous. And in fact, it's so onerous that it doesn't even make sense to connect with the bulk grid. And is there a world where NERC speeds up their process of coming up with their standards such that we could have more harmonized ramping and oscillation limits across the board, at least in the US? Is there? Do you think that'll happen in the next, say, quarter, 2 quarters, or what are you seeing in terms of how these standards are being developed? Because we can't. We have multiple targets to hit. This industry. Obviously we have to deal with the other countries as well, but even in the US, we have multiple targets we may need to hit, and it's not possible to design to multiple standards. So what is your perspective on this, given your active role in this?
Within the NERC realm, we are not going to have standards in the next quarter or two. I will tell you that. We will likely start drafting next year, but we're not going to have, all those done, unfortunately. The other thing to keep in mind is that NERC standards are a baseline. Every utility is free to set more stringent requirements. So just because we set a certain requirement doesn't mean somebody, I think you said ATC, they can't have their own more strict requirement.
So you don't think that'll settle anytime soon? At least for
the NERC standards process, while we do want to move quickly with it, and we are accelerating the work of the NERC LLTF as quickly as we can. And even then, it's a question of, is the first round going to set the number, or say that the regional reliability coordinators for that region should set it, because the grid is different in each place. What may be valid for ATC is not valid for Texas, is not valid for the East, etc. So
Thank you.
unfortunately, I don't think you're going to have those numbers in the next quarter or two. No.
All right, thanks.
Jesus?
Yes, hi. Excellent presentation. What I wanted to ask is that as more data centers have also battery storage and maybe generation, is there any consideration also for maybe VAR support and reverse power flow in this whole scheme, or is this not foreseen yet? I didn't see it in the presentation. Maybe I missed it, but that's a question that I have.
You say demand response?
Right. So if there's a possibility for generation at a data center, whether there is a question or a requirement for VAR support, or even reverse power flow, if there is any consideration there, or any rules for data centers with its own backup generation or possible backfeed into the grid.
Yeah, not as straightforward as standalone data centers. The DOE has issued a event notice of proposed rulemaking to the Federal Energy Regulatory Commission, which calls out co-located generation and load. That is something we have looked at a little bit in the NERC round, but part of that gets into market design issues and how these are treated and paired. In some respect, there's no differences between the standalone and co-located, but in some respects with the controls and protection coordination, there's a lot of differences. So either way, the facility is probably going to need to add through. It's going to need to have, ramp limits, and depending on the grid operator, not all grid operators are pursuing ramp limits. So I would say co-location could be a valid strategy for generation, just depending on the grid you're operating in. That one just needs a bit more work.
Thank you, Frank.
Thank you.
Yeah, this might be getting into the weeds a bit, but are we expecting during these faults? I expect when you're only dipping in 90% that you would just keep running constant power. But when we're dipping down to 50% or 40% and they want us to ride through this, are they expecting us to go like into a constant current mode, or are we curtailing power down to next to zero and then bringing it back on quickly? Like, what is the expectation from that regard?
So SPP said use constant current. I know ERCOT is specifically not taking a stance on that. So again, variability between grid operators. And I know at least in ERCOT, we've had discussions of, well, do you stay online and keep going through, or if you can go to zero but then return extremely quickly. I can't speak for ERCOT in this formal setting, but or at least for the policy. That policy is under debate in the stakeholder process. But odds are, we're looking for that kind of feedback, and I think both will probably be options. And so, yeah, if you can stay through or if you can return extremely quickly.
Yeah. So I guess from your perspective though, say I could pick either, I could go either way. It doesn't make a difference to us. would constant current be the better for stability for the grid?
I'll say that SPP wants to see constant current. I cannot speak for all grids in all situations. Yeah, and I know certain grid operators are not taking a stance on it, so that's where I want to be flexible right now. I'm not giving you a straight answer. I recognize that. Yeah.
Yeah, thank you.
Orange.
Lawrence, last question, and then.
Yes, actually, I mainly had also a very quick thought on this before. I think you showed it also to maybe combine battery with the SSD or the grid connection. I would suggest that we mainly also consider to take that a bit apart, because now that we're talking about DC, I think we can make the AC-DC connection, whatever it is, SSD, however we do it, as a kind of component on its own that has to follow these rules, whatever they are. But we can, in principle, design our DC system that it can continue to run with backup power batteries, whatever we come up with, because we anyway will have that. And then basically we only need, in the AC-DC conversions, need to deal with these rules that may be different in all countries or wherever it is. But then we can, with assets within the data center, we can, like batteries or supercaps or even demand response, so a load reduction from the server slowing down CPU, we can deal with whatever we need to keep stuff alive. And I think that's why I think it's super valuable to have these inputs. But I think really with DC, we can go much further than only thinking about what happens at the AC-DC stuff, but we can really see like, okay, we do whatever is good for the AC grid in the AC-DC stuff. And within our DC grid, we can make sure that our data center always continues to operate in whatever way is possible in this situation.
Exactly.
Contribution. Yeah.
Yeah. That's
Yeah,
for us.
Okay. Good. I think this was sparking some interest. So thank you, Eric, for being with us and sharing the requirements as seen with the eyes of a transmission system operator. Now we need to consider how we can incorporate and where the LVDC system can play a role. Now we have 11 minutes left, so maybe I ask a quick round to the workstream leads, whoever wants to provide a flash update, 1 or 2 minutes each workstream, to share with the rest of the people connected here where you are, how it's going, if you need more contributions. So let you decide who goes first.
I'd like to say something. Tony speaking.
Right.
Yeah. 30 seconds. We had a call on Monday on the main workstream, the main computer workstream, and I created a poll for people who wanting to writing stuff in the work documents, really like participating in writing thing. So I just wanted to share. I'm going to share here in the chat this link. So feel free, everyone here connected, to check 1 or few box or even 0 box. Not checking a box doesn't mean you won't be in a group. It just I'm looking for people wanting to write thing in a document. So that's it.
Thank you, Tom.
I can, Antonello speaking, can go next. Similar situation. I made a poll and we collected around 33 people. About half of them willing to contribute by drafting to draft the document, and half in reviewing the document. We set up a working draft where we are putting raw contents just to see what we have and what we miss. And we had a couple of calls and we are progressing. We also started, let's say, some more some deeper technical discussion in the last call. And that's all.
Thank you,
Okay,
Antonio.
then maybe let me go very quickly next. I'll very quickly share the one slide on the outline. We have been mainly, right now we have been on the polarities and system everything. We have, well, we had also some meetings. Also just yesterday we had the first more close, more active working session. We agreed for now on this kind of outline that we list all the possible polarities, bipolar, unipolar, all kind of variants of bipolar. Then we have a different aspect, that's the system working, TNS, IT. Then we have a third aspect, isolation. And then what we basically want to describe afterwards, then there's basically from these three things you can basically pick and combine. And there's going to be a lot of combinations, probably 16 or something like that. We will now in the first phase try to very quickly make all these different combinations and then discuss all of them, and then maybe put like the pros and cons, and then maybe select somewhere. I guess we will, it's not about choosing really something, but I think we will maybe exclude ones where nobody says that this might be interesting. But we'll keep with some options, and then especially try to find the synergies and what impact it has on different things. Also, we will do some fault analysis for these scenarios. And then we have last chapter is corrosion, which is a bit independent from that. Of course, it needs to be considered in the different things, but that is otherwise not that linked. So that's the status for right now.
Thank you.
I forget to tell that also in our workstream we define the table of content of the contribution.
Okay, who's next?
This is Lisa. I can go.
Lisa,
Hi.
thank you.
How are you? We met on Tuesday for the codes and standards workstream, and we are making good progress on the two key items that we've laid out, which are to get representatives from each of the organizations that are participating in the workstream. We now have most filled. We do have a few remaining, namely IEEE, and I'm still trying to lock down NEMA. But otherwise, making good progress. And you saw in the window, we did discuss that we do need to find somebody, I think, from the utility interconnection side. And we did just get a volunteer, it looks like from EPRI, which is fantastic. So making that update hopefully here to add that representative. And then I can just share my screen really quickly. We also finalized this input document to begin gathering the codes and standards from each organization. So we've laid out a full, I guess, a data architecture for which product categories we're talking about. And let me just pull up a sheet you can see. So for example, for us on the UL side, you would select a product type that you're talking about. By the way, if it's not a product type and it's a system standard, you can also select something like other. But you could select, circuit protection, and then you'd select the corresponding category that it is. You could throw a description in there of what it is. Is this a product or system standard? This one is a product standard. Write the code reference or standard in there, and then insert the link to the publicly available document. And then what we're doing is going through and actually saying, does this have currently existing requirements available for 800 volts DC? If it does not, you might say no. And this starts to show up as like a risk, right? Or this is an area that we're going to need to identify, highlight as an area that needs to get worked on. If it's yes, that would make it green. So that's good to go and can be used. So we have this whole file that we're working through. I'm just working on getting this transitioned into Google Sheets and then uploaded into our Google Drive. And we will start taking inputs and hopefully have a first chance to start reviewing those on our next call on, I think it's December 16th. And from there, we'll have a good assessment on gaps, areas that need to get looked at as a next step in progress for the white paper.
Excellent. Thank you, Lisa.
Yeah, you're welcome.
Lisa, Lisa, one
Yes.
question. Do you have someone from IC contributing in your work stream?
We do, yes. Uma is going to be
Okay.
representative. Yeah, she was on
Okay,
the
great,
line
great.
yesterday and confirmed, which is great. And actually, Antonello, we do need an official person from Current OS. I was just going to bridge for now, as I know which ones. I think there's 5 of them that we have technical.
But you are in Current OS.
Sorry?
You are in Current OS, so you already have a representative of Current OS.
Yeah. I was figuring between you and I, we can cover just entering in
Okay.
items in here. So I can grab you on that offline.
Thank you.
Yeah.
We can align. Thank you.
Great.
Brian,
Yep.
you want to share something?
Yes, I would. Let me go ahead and share my screen. Right. Hopefully this works and you can see my screen.
Yep, we can. Go ahead.
Okay, so yeah, just one all participants and one contributors meeting held so far. We shifted a little bit previously, but we're going to generally go with the Thursday time slot, alternating between all participants and contributors. We do have 8 contributors so far identified, and have made initial assignment on primary, secondary topics. Would be helpful in terms of requests to have some additional contributor participation. If you're interested, please send me an email. And especially in terms of the contributor participation, since the voltage touches both the IT rack as well as the incoming power potentially from SST, etc., would be great to have some additional hyperscalers included into the contributors. Also, I would just highlight that November 19th, our previous all participants in the sub project power distribution meeting, we went over some slides which were put together by Current OS on a number of topics, but especially highlighting a voltage proposal around 800 and potentially extending that toward 1500 volts as a straw man proposal would be great to get feedback. Feel free to also use that email address for that feedback. Also, then just a very quick look at the topics as we've laid them out so far, and look forward to those who are interested to participate in the next call tomorrow.
Excellent, thank you. And maybe JP, we close with you.
Yep. Okay. Yeah, we met 2 Fridays ago, associated with the architecture realigned on the different high-level block alignment. We're going to meet again this Friday to detail that outline. We have volunteers to support writing.
Okay. So we are at time, I would say, 15, so we are at 59. We managed to keep it in the planned slot. So I think it was a very, very interesting call. Thanks again to Eric for joining us and sharing those requirements. Thanks to all of you who joined the call. See you in a couple of weeks. And stay tuned on the wiki for the slides and the recording.
Thank you. Bye. Bye-bye.
Bye.
Thanks, everyone. Bye.
Thanks.
Thank you.